present afternoon.
Screen sharing, okay?
Okay.
Okay. My name is Shingo Kimura. I belong to Tokyo State University. I will give a presentation titled Automatic Conversion of 2D Images to 3D stereo. Oh, sorry. Yeah. Stereo images with variable disparity width using molecular depth images. As a research background, 3D viewing of images is often used in advertising, movies, and other media because it can enhance the sense of presence and immersion compared to 2D viewing. There are several methods for viewing 3D videos, but the active shutter 3D system is commonly used in movie theaters, as shown in this figure. This system this system uses two images, one for the left eye and the other for the right eye. These two images are projected alternately at high speed through a specialized projector. By using polarizing glasses synchronized with the projector, viewers can see only the left eye images when their left eye is open, and only the right eye image when right eye is open, enabling 3D viewing. However, to produce 3D images using the active shutter 3D system, stereo images are required. Consequently, movies captured with a monocular camera in the past cannot be viewed in 3D using this system. As a result, researchers have been exploring 3D stereo conversion, which uses image processing to convert molecular images into left and right images. The stereo images can be obtained by converting the left eye image to the right eye image. This conversion involves shifting and transforming pixels to account for the disparity, which is the difference in the way the human left and the right eyes perceive objects. The amount of disparity depends on the depth or distance of the object. As shown in this figure, the relationship between depth and disparity. Then it is defined by this equation from the dissimilarity of these two triangles. This equation relates the disparity D is obtained from the depth Z, the distance to the focal plane F, and the intercamera distance B. The relationship between disparity and depth is inversely proportional. The conventional method of 3D conversion, Deep 3D, is a widely recognized method for the transforming 2D images into 3D stereo images. This figure shows the concept of this method. This approach involves estimating the disparity between left eye and right eye image by using deep learning. The estimated disparity is used as the basis for pixel shift, which simultaneously performs pixel completion to create a right eye image from a left eye image. Compared to the depth image dataset, it is easy to obtain stereo image dataset because existing 3D movies can be used as datasets. Therefore, this method has the advantage of being easy to learn. However, there are some problems with Deep 3D. This figure shows an example of right eye image output from a left eye image using Deep 3D. But the human face is unclear. In addition, this model learns to estimate the disparity using stereo images. However, since no depth image is explicitly created, it is not possible to output images with a disparity gap of any desired width. As shown in this figure, the amount of 3D effect depends on the disparity shift width. Therefore, it is desirable to be able to adjust it. So the purpose of our research is to find a 3D stereo conversion method from 2D monocular images that is both clear and allows for freely adjustable disparity shift width. Then our proposed method is based on explicit depth estimation for 2D monocular image to estimate disparity, and then independent pixel shift and pixel completion are performed to create a disparity image. Since disparity estimation and pixel completion can be performed independently, the output image remains clear and the image with any desired disparity gap can be produced. This figure shows an overview of our proposed method. First, a depth image is created from the input image. The depth image is generated using a depth estimation method based on deep learning. Next, the depth image is sliced into individual depth images, and pixel shift is performed accordingly with them. Finally, the incomplete area due to the occlusion area completed under the right eye images is output. The following is a detailed explanation of the green box. The amount of pixel movement differs for each depth so that the slice of depth images is performed. Finalization is performed on signal depth pixels and other pixels, and each pixel movement area is determined. Then the input image is masked using each binary single depth image, and pixel shift is performed accordingly. The conversion equation for pixel displacement is determined based on the inverse relationship between disparity and depth. The amount of pixel shift for each depth is mapped to each depth by determining the maximum and minimum disparity. The pixel shifted images has incomplete area is the occlusion area. To address this issue, missing pixels are filled in by estimating pixel values from the surrounding areas that are not missing. In the experiment, we aim to evaluate the effectiveness of our proposed method in generating a clear right eye image with a variable disparity shift width from a single left eye image. Additionally, we plan to compare the accuracy of the generated images with those produced by Deep3D, a previous study. There are three datasets used in this experiment. The first is NJU 2K dataset, which are clipped scenes from existing 3D still movies. The second is the Kitty dataset, which are images of cityscapes from in-vehicle cameras. The third is the Sincere SF dataset, which is CG images of cityscape from an in-vehicle camera. Our proposed method uses trained model of BMD for depth estimation. This model was trained using a dataset of depth images. As for completion, a neighborhood-based completion method called TELEA is utilized. This figure shows the result of generating right eye images from left eye images using the conventional and proposed method on the NJU 2K dataset. This is the input left image. And this is right image output by Deep3D. This is the right eye image output by our proposed method. And this is the correct right image. Our proposed method generates clearer images than the conventional method. The clarity of people's face is improved. And this is Kitty dataset's results. And this is Sincere SF dataset's results. From these results, our proposed method generates clear images than the conventional method. Next, this figure shows the output results for different disparity widths using our proposed method. The output images shows a larger disparity shift width as it goes to the right. And this is a GIF image of the result of these outputs. And the shoulder area shows the different disparity width shift width can be reproduced. While the conventional method can only reproduce disparity that depends on the dataset, our proposed method uses depth estimation for disparity estimation and can generate right eye images with variable disparity width based on the conventional equation between depth and disparity. This was verified through our experiments. Finally, we summarize our presentation. We proposed a method to create 3D still images by calculating disparity based on depth estimation using deep learning. Compared with the conventional method Deep3D, Our proposed method can create clear disparity images in variable disparity width. This concludes my presentation. Thank you very much for your attention.
Thank you. Very nice results and good work. Thank you.